Welcome to this lecture in this course, Electricity in Daily Use. In the last lecture, we discussed earthing and different aspects of electrical safety. So we will continue this discussion, and today we are going to discuss a typical wire layout in our homes. So if you see this figure in front of you, you see that there is this electricity pole which is the from the utility. In our case, the utility is the PDD or the Power Development Department. From this electricity pole, two wires come in. One is the red wire and one is the white, black wire. This red and white, however, is just symbolic, just to represent. So these two wires, one wire is the live wire L, and the other one is the neutral L and N. So live wire and the neutral wire. Between this live and the neutral wire, there is a potential difference of around 230 volts, and this is an AC voltage. These two wires go into the electric meter, which measures the consumption of electricity by the end user. From this electric meter, the two wires go into what is known as the MCB, or the miniature circuit breaker. The miniature circuit breaker is basically a device which is used to cut off the supply in event of a short circuit. MCB, let me write here, MCB is a miniature circuit breaker. Okay, and it is used to cut the supply in the event of a short circuit. By short circuit, we mean a condition when the live and the neutral wires join and excess amount of current flows through the circuit. The next part after the MCB is the RCCB, or the residual current circuit breaker. This is to prevent against leakage currents. This is another protective device which is used to prevent any leakage currents that may be present in the circuit. Now this MCB, as you see from this figure, it is a double pole. It is known as a double pole MCB because it disconnects both the live and the neutral wire. In contrast, if you see this type of MCB, this is known as an SPMCB, or it is also known as a single pole MCB. Single pole MCB. It is called a single pole MCB because it only connects the live wire. It only disconnects the live wire. It does not interfere with the neutral. Okay. So in this figure, you see that once the electricity reaches the MCB, it then goes on to the single pole MCBs, and these different MCBs are used to connect different ends of the different end products or end loads. Okay, so if you take the example of any one MCB, if you take the example of this one, this wire, this takes this route and it goes to this switch, and it goes to this switch. So on this MCB there are two switches. These two switches light up these two bulbs, bulb number 1 and bulb number 2. So the live wire is connected to one end of the switch, and from the switch the wire goes to the bulb, and the other end of the bulb is connected to the using this black wire, it is connected to the neutral like this, and this neutral is then internally connected to the RCCB, and this is connected to the MCB and backwards like this. So if you see the red wire which let me use a different color for the red wire. So this red wire, this goes like this goes like this, and then this is the red wire, and the orange color wire that I'm showing, or the black wire that I'm showing, is the neutral wire. So current flows through the live wire and it goes starts from the live wire and it falls comes back through the neutral wire. So this is the typical layout of a house. So similarly, if you see, there are what are the different loads that are connected in this circuit. You have the lamps, right? you have you have a water heater here, you have a water pump here, you have some other heating switches here, right? So this is another plug socket. So this is here we have a normal switch is a one-way switch. Then you have two-way switch which you can connect at two different points and then turn off at two different locations. So this is the typical layout of the electricity wiring in a house. Okay. Now, when we talk about house wiring, you have to see that basically this is a conductor, copper conductor. As I have mentioned in the previous lecture, copper being a very good conductor of electricity is preferred for conductors in inside the homes. So conductor is copper. So this copper is in the form of wires. Now, if you have ever sort of got an electrician home, you would have noticed that he usually asks you to get different types of wires. He sometimes asks you to get a 1 mm. He says 1 mm, but it's actually 1 square mm. He says 2.5 mm, but it's actually 2.5 square mm, 6 square mm, and like so. So what is that basically? That is the cross sectional area of the conductor. So this conductor, which is if the cross sectional area of this conductor is basically what this square mm reading is actually. So every wire has based on the cross sectional area on a standard. It has a number of conductors. Here it's 14, and so 1 mm wire will have 14 conductors, thin conductors, each with a diameter of 0.3 mm. So this 14 and 0.3 is 14 conductors, and each conductor has a diameter of 0.3 mm. Okay. So then you have the insulation. So this this 0.3 mm is the diameter of the strands together. Okay, so 14 conductors together form 0.3 mm the diameter. Then you have the insulation, which is of 0.7 mm thickness. Okay, then you have the diameter, overall approximate diameter. But what I want to say here is that this each of these wires corresponds to each particular current rating. So if we select this 0.1 square mm wire, it has a current carrying capacity of about 15 amperes. So 15 amperes means it can at max bear a current of 15 amperes. This rating is 15 amperes. And this conductor, this 1 square mm conductor, has a resistance per kilometer of 18.10 ohms per kilometer. So if you have this conductor spread over 1 kilometer, the resistance of this conductor is going to be 18.1 ohms. So you don't need to remember all of this, but it's always good to know. You should know what these stand for, but it's not always necessary to remember all of these values. And similarly, for this is the table for higher thicker wires. As you see, the current rating of these wires goes on as the diameter of the conductors increases. So after we talk about wires, you would have seen sockets and plugs in your houses. So if you see what a socket is basically that terminal in which devices are plugged in. Okay, so these sockets and plugs in our homes are rated for 230 volts AC, and 50 hertz is the frequency. The current rating of the socket, usually we have three types of sockets. We have this 5 ampere socket, 15 ampere socket, and 25 ampere socket. Okay, so this is an example of a 5 ampere socket. So when we say 5 ampere, that means the load that is connected on this socket should not exceed more than 5 amperes. The current of the derived by the load should not exceed more than 5 amperes. Similarly, you have this socket. If you see, this has two holes, this has three holes. So this socket is rated for 15 amperes. And then you have this socket, the third one, which has a slightly bigger hole here. This is the 25 ampere socket, and this is what is known as a heating socket or a heating load. For in this socket you usually connect geysers, right, heaters and other loads which consume a lot of energy. All right, so based on these sockets you have different types of plugs. You have a type C plug, which is also known as a two pin plug. You have the type D, which is the 3-pin, this one, and then you have the type M, which is this one, which has a slightly bigger third terminal. This third terminal is bigger because it is meant for earthing. So it is always recommended to do earthing of the heating equipment or heavy electrical equipment. Okay, now suppose you want to select a particular socket and wire in a particular room. So what we do, we basically try to make an assumption or make a guess of what the load is going to be. So suppose we have two incandescent lamps, incandescent bulbs. By incandescent bulb we mean those bulbs which used to be present in the olden days, the ones with the yellow light, which used to have a filament, this filament, and this used to be, like this, and it used to have a whole this body, and this used to go into the holder. So this is the incandescent bulb. So suppose you have two incandescent bulbs, you have a fan, a blower, and an electric iron to be used in the room. Okay, so all of these devices would be rated for 50 hertz and 230 volts. Okay, so this is the voltage rating. So these devices should be run at this voltage and this frequency. Now, based on how these devices are designed, they will have different resistances basically, and based on these resistances they will derive different powers and consequently different currents. Let's see what that means. The bulb is said to be 100 watts. Okay, and this is supposed to be 230 rated at 230 volt. So if you see a 100-watt bulb at 230 volts, like I've said earlier, P is equal to V into I. This is the instantaneous value. So if this is 100 and the voltage is 230, so the P instantaneous value of I should be equal to 0.434 amperes, right? So this bulb carries a current of 0.434 amperes when it is run at 230 volts. So if you have two bulbs, this current rating goes on to multiply by 2, you get 0.87 amperes, right? Similarly, if you have a fan which is rated at, which the fan says that it's 70 watts, and that fan means that it is 0.4755 amperes. A blower which is 2000 watts is 8.7 amperes, and an electric iron or an electric press is 1300 watts and it carries a current of 5.65 amperes. So if you see, the total current to be supplied by the source is equal to the sum of the currents. It's 0.87 plus 4.4755 plus 8.7 plus 5.65. So total comes out to be around 15.7 amperes. Okay, so this is based on the assumption that all of these devices are simultaneously connected to the supply. So okay, so what you can do is you can go to the table here, and you can see what is the See, if you select a if you select a 1 square meter current, it is rated for a current of 15 amperes only. So it has to be a little higher than that, right? Because if you add another device to it, it will not be able to bear that, and it's not recommended to overload wires. So what we do, we select a current, a wire which is next higher in this table. So what wire should we select? We will select this 1.5 square wire because it easily can sustain a load of 18 amperes. Okay, I hope this is clear. So for 15.7 amperes, we select this 18 ampere wire. And if you want to be more cautious, you want to be more secure, you will use a still higher wire. So you can use in practice, you will see 2.5 square wire is also recommended to be used. So if you see 2.5 amperes, it's 2.5 amperes is carries a current of 25 amperes. So for more safety, it is recommended to use a slightly higher gauge of wire. Okay, so 2.5 carries a current of 25 amperes. Okay, so what is the heating load in our case? The heating load is 8.7 and 5.6, so that means a total of 15.35 amperes. So what should be the socket like? The socket must be either D or M type, like we discussed here. It should either be D type or it should be M type. Okay, because it has to carry a current of around 15.3 amperes. Okay, so this is about choosing plugs and sockets. Now, when we use different devices, we all use different devices in our homes. So they are rated to be run at a particular voltage, 230 volts and 50 hertz. And at this 230 volt, their power ratings are defined. Power ratings are defined, and this is usually done by the manufacturer himself. Okay, so from these parameters, you can calculate the current and see how much current is required to be, how much current the equipment is drawing, and based on that current, you actually select the wire size in your homes. So in case of domestic use, power P is equal to V into I into cos phi. So this is a term which we have not talked about before. This is in use, this is in AC circuits. When we were discussing AC circuits, I forgot to mention this point. The power in AC circuits is actually V into I into cos phi, where this phi is the angle between the voltage and the current. Okay, and typically the PF, these power factor values are like this. So it is usually 1 for heating loads, it is 0.9 to 0.95 for transformers, and about 0.8 to 0.85 for electric motors. Also, once you have this P and V, you cannot straight away calculate the current. You have to see the efficiency as well. So efficiency means the power output by power input. Right? So if a motor is 80% efficient or 70% efficient, accordingly the power rating has to be, then you have to divide by that term. So the for calculating the current of a electric motor, we will simply say it is the electric current derived by the motor is P divided by voltage into power factor into the efficiency. Okay, so higher the efficiency, lower will be the current, right? So lower the efficiency, if your efficiency is higher, current drawn will be less, and if your motor is less efficient, current drawn will be more. Okay, similarly, if you have low power factor, let's say around 0.5 or 0.6, very large current will be drawn. If you have very good power factor, let's say 0.9 or up to 1, then a lesser amount of current is going to be drawn. And this is power for three-phase circuit. I will not touch this here because we have not discussed three-phase circuits, and I feel it's not necessary for this course. So let's take an example of an electric iron. Electric iron, let's say this is a typical electric iron. It says the voltage is around 1300 watts and the voltage rating is 240 volts. Okay, this is the specified by the manufacturer, but you can use it safely at 230 volts. Okay, so since this is the heating load, since this is a heating device, the power factor is taken to be 1, and since it does not have any motion, so we don't have to see the efficiency. So for current what we do, we basically divide the power, that is 1300 divided by 240 into PF. So this current comes out to be 5.41 amperes. Next, let's talk about a rice cooker. A rice cooker, say, has a power rating of 1000 watts and 230 volt 50 hertz. So this again is a static device, no efficiency issues, and the power factor is again 1. So this derives a current of 4.35 amperes. Next, you have a water heater or a geyser, right? So this geyser is 230 volts, 2 kilowatt. By 2 kilowatt we mean 2000 watts. Okay, so 2000 watts, when you run it at 230 volts and power factor 1, so it derives a current of 8.7 amperes. Now see an interesting thing. This is 2000 watts. When you run this same machine at a lower voltage, let's say 200 volts only, what happens? I is higher. It happens 2000 divided by 200 into 1. So this comes out to be 10 amperes. So if you decrease the voltage, what happens? The amount of current drawn by the device increases. Okay, so this is why it is always recommended to run the appliances at their recommended or the standard voltages. Okay, so this was about a water heater or a geyser. Okay, then you have an induction heater. Induction heater, as you know, is again a heating device, but it is used as a to heat devices. But for induction motor, I think the power factor, this is a mistake here, so it has to be 0.9 here, 0.9 to 0.8. So accordingly you will work out this calculation. So the purpose of showing you this is basically I want you to see how if you look around and you look at the various devices that are used in your homes, you will be able to see the power rating, the voltage rating, and then ultimately be able to carry the calculate the current. So now let's see a domestic water pump or a water pump. What does it do? It basically lifts up water, right? So if you see the kilowatt or the horsepower rating, it's 372 watts and it's supposed to be run at 220 volts. The power factor is 0.8 and the efficiency is 0.8. Again, we take the efficiency as 0.8. So it derives a current of 2.65 amperes. Induction heater, so we have done this already. So mixer grinder, okay, again a motor, a moving device, it has a motor installed inside it. So for that also you can calculate the current rating, right? 4.75 amperes. Now incandescent bulb, you have let's say it's a 150 volt 100 watt bulb. So what happens if you run this? What is this? What does this bulb do? Let's say you have a bulb B1. Let's call it bulb B1. It is at 100 watts at 150 volts. So what is the amount of current that this bulb is going to draw? It's going to draw 100 divided by 150, and that is equal to 0.66 amperes. You have another bulb B2, which is at 200 watts at 220 volts. This derives a current of how much? It derives a current of 100 divided by 220, that is 0.455 amperes. I2, this is I2. if there are, now one thing that you have to note here, if there are two bulbs of the same voltage rating, the bulb having the higher power rating will go brighter when connected in parallel, and the bulb having the lower power rating will go brighter when connected in series. So you have two scenarios. You have bulbs with the same voltage rating but different power ratings. Okay, so if you have two bulbs of different power ratings, the bulb with the higher power rating will grow brighter. Why? Because it derives more current from the system, right? And similarly, if you have the and if you see in case of series, the one with lower power rating will grow brighter because it is running at a current higher than its actual rated current. So this is about some basic electrical devices that are used in our homes. Okay, I don't want to talk about transformers to you, or maybe we can just see. Okay, let's talk about a transformer or a stabilizer. You know, we almost everybody has a transformer or a stabilizer in their homes. So what is a transformer? So a transformer is basically a device which steps up voltage or current. Steps up voltage. For you it's sufficient if you remember this, if you know this. Steps up or down the voltage. Okay. So if you look at your locality, you will see a transformer which is known as a step down transformer, which reduces the voltage from 11 kV and brings it down to 415 volts between two phases, phase to phase. So this is actually this 230 volts that you get when you see it with respect to the neutral. Okay, so the in case of transformers, okay, I think this will be too much for you to understand. I think we best skip this transformer part. So just so you know, in case of transformers have this relation. The V1 and V2, which are the two voltages, is equal to N1 and N2, and this N1 and N2 is also related to the two currents inversely. Okay, so if you are given V1 and V2 and you are told what is the turns ratio, which is this N1 to N2, you can calculate this. Or if the turns ratio is given and one of these voltages is given, if you are asked to find out what this voltage is going to be, you can easily find it from the formula. The next device that you usually use in your washing machines, in your homes, are washing machines. So for a washing machine, it says 340 watts. It takes 340 watts to wash, okay, at 230 volts, 220 volts rather. So the power rating is 340 divided by 220, and the power factor is 0.8 and the efficiency is 0.8. So in case of washing, it takes 2.42 amperes of current. When the same machine is used for spinning, as in for drying, the power rating is reduced, so it derives only 1.1 amperes of current. When you go for wash and spin both together, so in that case the power rating is further higher, and the total amount of current drawn by this machine is 3.5 amperes. Now a television set is 33 watts, and its power factor is 0.8, so it derives a 0.19 ampere of current. Similarly, if you have a same television at a lower voltage, because it says that it supports 100 to 240 volts, right? It has a wide voltage range. So if you run this at 240 volts, the current drawn is going to be 0.19 amperes, and if you run it at a lower voltage like I discussed earlier, the same current is going to be 0.42 amperes. A CFL or a LED, compact fluorescent lamp, or a light emitting diode, LED, light emitting. These are two types of lamps, LED lamps and CFL lamps. So again, if you see their specification sheets, 7 watts at 220 volts. So you can see that this derives a current of 0.036 amperes. Now for an inverter or a UPS, which we have in our homes, UPS stands for uninterruptible power supply. Okay, this inverter or uninterruptible power supply is used to provide power in case of an outage, in case there is some outage. So in that case, if the VA rating of the inverter is, VA is basically the product of V into I in case of AC circuits. In case of DC circuits, this is the simple power, but in case of AC circuits, this VA rating is just the product of V and I, and when you multiply this VA rating with the power factor, you get the actual power. Okay, in AC circuits. So if you have a inverter 1100 VA, and if you run it at 230 volts, you get a current of 4.8 amperes. Okay, so 100 watt, if you run what are the different equipment that you can run on the inverter or the UPS? You can run the incandescent lamp, 100 watts. You can run 11 incandescent lamps. Okay, you can run 133 LED TVs, with each LED TV having this much current. Okay, so 25 televisions on this 1.1 kVA inverter. Okay, and one water pump you can run on this. Okay, so this is about it, and this is about the inverter. Now once you have this, once you use electricity, of course your electricity is not free, nothing is free in this world. So you will be basically charged for the electricity that you use. So this electricity bill is what is known as electricity tariff. It is that amount of money that is chosen or framed by the supplier, and the supplier charges you for consuming that much electricity. So I don't know, I will elaborate this further in the next lecture, but just for brief introduction, there are two types of tariff. You have a flat demand or flat rate tariff. Like I said earlier, you have electricity meter. That meter basically measures how many units of electricity you use. So if you have an electric meter, it basically has a block meter tariff. So in flat demand tariff, irrespective of the number of units used, you are charged, let's say 0.5 kilowatt, you are charged 365 rupees per month. This is flat. Okay, and block meter, if you first consume 100 units, for the first 100 units you are going to be charged 1.54 rupees. For the next 100 units you are going to be charged 2 rupees per unit, and for still higher, if you are exceeding 400 units, then the consumption is 3.50 for the still higher units. And lastly, before we conclude, the various companies that provide electricity or major utility companies in J&K. This is the J&K State Power Development Corporation, JKSPDC. This is the power producers. You have the NHPC, National Hydropower Corporation, and the Northern Grid, which is the interconnection of various grids. So these utilities, these power generation companies, they provide the power to the state or through these companies: the Power Grid Corporation of India, Sterlite Technologies, this is a private entity, and Kashmir Power Transmission Corporation Limited, KPTCL. So with this we can come to the end of this lecture. I will now see you in the next lecture, and we'll take this course further there. Thank you.